Hi, Dr. Graham Blackwell here from the Institute for Harmonious Science with another topic from the cutting edge of 21st century physics. Today's topic is gravity and how it works. Or should I say, how it's most likely that it may work given all sorts of things that we already know quite a bit about. Gravity is one of the great mysteries of the universe, which is quite surprising when you think that actually it's gravity that shapes the universe at just about every level. Einstein told us that gravity is actually curvature of the fabric of space-time, humps and dips in that fabric. But we still don't know what that fabric is, how it is that the planets and stars and even whole galaxies shape that fabric, and why it is that everything in the universe, even light itself, follows the contours of that fabric. There are other things as well about gravity that have puzzled scientists for quite some time. Like, why is it that gravity is so much weaker than every other force in the universe? 1,000 million, billion, trillion times weaker, for example, than electrical forces or magnetism. And why is it that gravity always acts in a positive direction, always attracting, never repelling? And why? Okay, let's look at those two questions first. What if, just if, gravity isn't actually a single force at all, but the tiny difference between two much larger forces acting in opposite directions, one attracting, one repelling? And what if the attracting force is always just that tiny bit more than the repelling force, so that the result always acts in an attracting direction? That would do it, wouldn't it? And what if, just if, those two forces are ones that we already know about, or think we do? Then we wouldn't even need an extra force called gravity at all. Nonsense? We'll see. We're going to do a little thought experiment. Einstein was very keen on thought experiments. This one's about static electricity. You know, the stuff that makes balloons stick to walls, makes tissue paper stick to combs, and makes your hair stand on end if you brush it vigorously on a very dry day. Static electricity is caused by charged particles, protons that carry a positive charge and electrons that carry a negative charge. Charges of the same type repel each other. Opposite charges attract each other. That's why negative electrons orbit around an atom's centre, or nucleus, that's made up of protons. There are other particles in the nucleus of nearly every type of atom too, called neutrons, because they're neutral. They don't carry any positive or negative charge. Or do they? Let's take a closer look. Protons and neutrons are each made up of three smaller particles called quarks, or quarks depending on which physicist you talk to. A proton has two quarks, each with a positive charge of 2 and one with a negative charge of 1, giving a total of positive 3. We're counting in thirds of the full unit charge for a proton or electron, so we can stick with whole numbers. A neutron has the same type of quarks, but a different mix, just one of the positive 2 type and 2 of the negative 1 type. That tots up to an overall 0. No excess of positive or negative. But let's not overlook the fact that there are positive and negative charges in that quark mix. So how does that all work when we put two neutrons side by side? Well, of course, the positive quark in one repels the positive in the other. The negatives in each do the same, and each quark in one neutron attracts any opposite quarks in the other. You can see that here. Blue lines are attractions, red lines are repulsions. To find the attracting or repelling force, we multiply the numbers at the two ends of each line together. So, attractions, 2 times 1, 2 times 1, 1 times 2, 1 times 2, total 2 plus 2 plus 2 plus 2, or 8. Repulsions, 2 times 2, and 4 lots of 1 times 1. Total 4 plus 1 plus 1 plus 1 plus 1 gives us 8. There you go. 8 units of attraction, 8 units of repulsion. It all balances out, no net effect. Just that teeny tiny gravitational attraction between those two neutrons still to explain. But hey, we're making a pretty big assumption here. We're assuming those units of attraction and those units of repulsion have exactly the same strength. How do we know that? We don't even know what causes that attraction or that repulsion. Some of you will have heard about virtual photons. That's a handy way of describing what seems to be going on, but it doesn't explain it. There are in fact good reasons why those two effects probably aren't equal, why the force of attraction could well be just a tiny bit stronger than the force of repulsion. That tiny bit, that tiny excess of attraction over repulsion, could be the effect that we call gravity. There are those of you out there who know a bit about stuff who must be now thinking, that can't be it. That can't possibly be it. There are at least 5 good reasons why that can't be it. Let's have a look at those 5 things, one at a time. First, even if we count up all of those bits of charge in a neutron, ignoring whether they're positive or negative, they still tot up to less than twice the charge on an electron. And the gravitational pull of a neutron is nearly 2,000 times the pull of an electron. You'd need nearly 2,000 times that tiny difference, 2,000 times the total combined charge effect. In fact, you'd need every bit of the mass of a neutron, or anything else, to take part in that charge effect, because the gravitational pull of anything is proportional to its mass. OK, back to that neutron. We already know that a quark isn't the end of the story. In a standard radioactive process known as beta decay, a single quark splits into 2 parts, positive and negative. So we know that even a single quark has both types of charge up its sleeve. But we can go much further than that. We know that matter is just a form of energy. Einstein told us that with his E=mc². And there's a lot of research evidence to support the idea that particles of matter are just photons of electromagnetic energy, like light or radio waves, wrapped round into tiny bundles. Every photon can be seen as a combination of energy spinning clockwise and anti-clockwise at the same time. That's standard textbook stuff. And there's also research which suggests that energy spinning clockwise will give us one type of charge, whereas anti-clockwise energy gives us the opposite type of charge. In that case, every bit of energy in any particle contributes to the positive and negative charges in that particle that between them give the overall charge. This means that every bit of energy is contributing to that tiny difference that could be responsible for the effect that we refer to as gravity. So in the case of the neutron, 2,000 times as much mass gives 2,000 times as much energy, 2,000 times as much charge, positive or negative, 2,000 times as much tiny difference, 2,000 times as much gravitational effect as an electron. Next question? Well, the obvious one is, electrical and magnetic effects can be blocked by suitable materials. So if this is the way gravity works, how come it can't be blocked just as easily? Answer. Yes, it's true. Classical electromagnetic effects can be blocked. But at the quantum level, electromagnetic potential cannot be blocked by anything. A standard feature of quantum physics, the Aharonov-Bohm effect, shows that at the quantum level, electromagnetic potential can create interference effects that cannot be blocked by anything. Gravitation is an interference effect, acting on the waves that make up particles, so gravitation cannot be blocked. Right, the big one. Why should there be that tiny difference between attraction and repulsion that gives an overall attraction effect? Well, first, let's remember that there's no scientific reason why those two forces should be the same. So the fact that a tiny difference of this sort fits in with all the experimental evidence is a good place to start. In fact, we could put the question the other way round and say, why do we need to start inventing some mysterious force when in fact all the evidence is explained by forces that we already know about? This isn't the place for a deep technical investigation or explanation, but it's perhaps worth noting that a force that tends to move something away from electromagnetic field strength is different from a force that tends to move something towards electromagnetic field strength. That's relevant. That brings us about full circle. So what's this curvature of space-time that Einstein talked about? Well, if you have a two-dimensional landscape and you want a few hills and valleys in it, you need a third dimension for those hills and valleys to go up and down in. In the same way, if you have a three-dimensional spacescape and you want a few humps and dips in it, you need a fourth dimension, a fourth spatial dimension for those humps and dips to go up and down in. And I've never heard anyone suggest that gravity is a fourth spatial dimension. No. The way to get the effect of ups and downs in 3 dimensions is to vary the texture. And that's exactly what this description of gravitation does. Near to large objects such as suns or planets, the electromagnetic texture of space is very strong. There's a strong electromagnetic field, whereas far away out in deep space, the electromagnetic texture is much weaker. This gives the effect of ups and downs in the fabric of space-time. This explanation of the nature of those humps and dips fits exactly with the observed evidence. Just one more thing. According to relativity, any explanation of gravity has to fit in with something called the Lorentz transformation. How does this version of gravity stack up against that? If you see particles of matter as closed-loop bundles of energy, then all the proven findings of relativity fall out very neatly, just like clockwork. But this view also puts a slightly different angle on the Lorentz transformation, and from that angle, this view of gravity also fits very neatly. All of this is explained in detail in my paper on gravity published last November. You can buy a copy from my website if you're into that sort of thing.